Hello, my name is Paul Wallace, and I've been asked to give you a quick update on what we've been up to in the AI space, particularly around deploying of large AI clusters and storage for large language models. Now, obviously, you've heard throughout the conference today, HPC and AI are both great areas of growth for us here at DDN. We presented a slide similar to this one last year, but it's grown dramatically. And today, DDN is powering well over 200 or maybe 250,000 GPUs now in large-scale AI and HPC systems. In particular, the NVIDIA A100s and H100s right the way across different industries, pretty much any industry in the commercial space, academia, government, in all sorts of use cases. So if I showed you this slide a year ago, it had about 50 to 60,000 GPUs. And over the last year, we've seen this fast and furious growth of adoption of deep learning throughout all industries. And that's been driven in part by large language models. And if you look at this snapshot of logos, we're pretty much from the very largest AI programs in the world, all the way through some of the smaller, very innovative groups, all depending on DDN storage. And what's interesting is that a lot of these customers are working on their third or fourth generation infrastructure with us, all the way from single servers all the way to tens of thousands of GPUs. So there's this giant growth and market velocity, much of it being driven by large language models. And obviously, we've all heard about some of the common GPT families like Nemo, Megatron, and all the very large models. However, in order to develop these systems, whether it's foundational models or fine-tuning of existing models, or maybe taking an existing foundational model and fine-tuning it for a specific task, it requires a lot of computing power. And really, that acceleration for computing needs to be matched with accelerated data. And so ultimately, DDN is behind a lot of the infrastructures enabling development, design of these foundational models, moving right the way through into production at scale. We're often asked the same type of questions at DDN, actually. Why should we choose DDN for AI? Why are DDN so successful? And how is it that DDN's managed to drive this entire space? And it all comes down to three things. The first one, obviously, is performance. We've spent a lot of time aligning our entire stack, software and hardware, with the GPUs. So when you've got GPUs powering all sorts of applications, either HPC or deep learning codes, you've got a tremendous amount of concurrency. And we're able to handle that concurrency very, very rapidly, but also very efficiently through the clients, through the networking stack, and all the way down to the storage in our appliances. And that ability to handle that data gives us a tremendous amount of performance and efficiency. So we capture both the reads and the writes, delivering both very rapidly, very efficiently. So our ability to handle that concurrency, our differentiated technology, is part of the reason we've managed to be so successful in that space. So when you think of DDN and why we're doing so well in AI, it's because we've got this unique differentiated technology. You've got a whole group of DDN technologists and engineers here at the show that can dive into the detail of this, but you should know that for customers like Mark Hamilton, who you heard from earlier, with whom we design and run these very large machines at NVIDIA, they chose DDN because ultimately they get more speed, more performance under their workloads because of our technology. But at the same time, they're more efficient. And that means faster time to train these large models and also cost savings and so on and so forth. For the second point, all these large language models become large data problems, at scale data problems, and it just so happens to be our key focus. We're dealing with very large volumes of data. We need to move this data very rapidly, and more importantly, we've got to hold on to that data for very long periods of time. So there's all these complex at-scale questions to which we bring a tremendous amount of experience and expertise. And the last piece of why we do so well in this LLM space is that we're in a forward-looking position. When you compare us to all the other storage partners, we're in a place because of our relationship with the accelerated computing companies like NVIDIA, where we're working with them months before they release a new chip, a new accelerator, a new reference architecture. So we've got this very deep joint engineering time ahead of the release of the accelerators. So when they hit the market, we've got very tight integration, unique integrations. And so we spend our time with customers looking at the AI codes, looking at the applications you're running and being exposed to that problems. So not only do we have really tight integration with the accelerators themselves, we hear from our customers directly what kind of challenges that they're facing when they're running LLMs at scale. And so that essentially turns into new features that we deliver with a tremendous amount of velocity and a rapid response. All those things combine to deliver better technology, being focused on the problems, and rapidly iterating within the industry allows us to lead into all those things. So one of the most common misconceptions when we talk about AI, a lot of people will hear, especially when it coming from some of the other storage partners, is that AI is all about reads. So it turns out that AI is actually a mixture of both reads and writes. It's very important we deliver both read and write performance evenly. And that's one of the key points of our DDN platform, what we bring to the market. This slide shows some research, I think, from Oak Ridge National Labs. They did a study on one of their largest deep learning systems, I think 23,000 machine learning jobs, 9 different disciplines and sectors, all sorts of different applications of deep learning codes. And they demonstrated that both reads and writes were happening, approximately a 50-50 mix. So the write component turns out to be an extremely important part of the AI puzzle. There's a lot of similar research out there, so you'll see that across the industry as a whole, clearly illustrates you need both read and write performance. And that's what we do really well. That's why we invest so much of our focus in the ability to handle balanced performance for both reads and writes. And so our storage platforms are able to handle both equally at scale. And here's one example where writes are incredibly important. We've heard a lot about checkpoints today. And this is another thing that's come up quite a bit, another common misconception. So for those of you that are in HPC who may not be familiar with checkpointing, you can think of checkpointing as like saving your work. The most obvious reason why you want to do that is because you're going to hit some kind of a fault, whether it's hardware or software. You're going to run these big jobs for long periods of time, days, weeks, and more, and there's a risk that you're going to hit some kind of a fault. So you want to save your work regularly. So that's one reason to write a checkpoint, to dump your models from memory straight into disk, hence the write component of that other chart we just saw. But I think one of the important things that I want to stress is that when it comes to AI and deep learning, checkpoint is actually part of the actual training workflow. It's an important inherent part of that workflow, and so it allows us to do different things with our models. So when you think about a thing called transfer learning, you're going to be spending a lot of compute time building a model for a specific application, but at some point, you might want to transfer that model to another space. So you take a checkpoint of memory onto disk and transfer all that learning onto a different application. So for example, I'm building an application that's really good at chemistry, perhaps, and then I want to build an application that's really good at cooking. So I can take that same transfer, I can take those same basic parameters that I've trained 80% of the way, really good for chemistry, and it turns out I can actually apply them to my cooking application. So it's important to be able to save my work on the chemistry. I checkpoint the models, I transfer them to a different application. And being able to load those into memory very quickly enables me to make the most out of the training process. And so this idea of checkpointing becomes even more important. Another important illustration actually is that of the accuracy problem, as in this chart here. When you're training a new model, you're constantly reading and processing the same data set. Over time, your model gets more and more proficient, but at some point it becomes more and more accurate. However, at kind of some point, it meets a curve. You get to a tipping point where you've overtrained and you become less accurate. And that's an inherent natural part of the deep learning process. So by checkpointing regularly, by being able to save your work regularly, your data scientists are going to be able to wake up one morning, look at all the work that was done overnight and say, hey, we've overtrained. So let's go back a couple of checkpoints to the moment where we had that most effective and valid model in the history of all the runs we actually did. So you've got all these capabilities that come around and point to the critical need for checkpoints. And so ultimately, this goes back to that ability to read and to write very efficiently. Our customers implement AI and deep learning with DDN platforms, not only because they're able to deliver performance much more rapidly, but also if you look at the top right, when we look at our ability to read and load data sets very rapidly into GPU memory, but also write frequent checkpoints very rapidly. We're talking about terabytes of data every time you save a checkpoint. And when you compare that to other storage providers, DDN can do that around 5 to 12 times faster than any other storage providers. So we give that efficiency right back to you and your systems. Going back to the LLM part of the story, when you're building those NVIDIA SuperPod systems that Mark Hamilton talked about, you're investing tens or hundreds of millions of dollars worth of computing infrastructure when you use DDN, and by being more efficient in the way you're able to deliver your data for reads and for writes. Those savings become real performance points that ultimately save you a lot of money, put a lot of money back in your pocket, save you time, and allow you to increase that velocity. So those are the trends that we see. Just to close, moving forward, we recommend you take a look at the reference architectures we've created with NVIDIA. We've got some updated reference architectures on the way as well that are built on this work, where we provide really strong guidelines with clear examples of deployments that we've done over time. Those guidelines for reads and writes also include recommended performance metrics for the GPU usage. So these reference architectures, they're available online, or you can download them. Talk to your DDN sales engineers for more information. We've got a lot more great content around this and other similar use cases.